In this video, we're going to talk about measures of position, in particular, the z-score. First of all, measures of position are commonly used numerical summaries of data to specify the proportion of data that is less than a given value. In other words, where does that particular data fall in our entire data set? We're going to first discuss the z-score. The z-score is going to tell us how many standard deviations an individual data value is from its population mean. So we're going to be comparing it to the population mean. Now, z-scores can be positive or negative. The reason z-scores can be positive or negative is because we're talking about where does it fit on the spectrum compared to the population mean. And so when we think about this, if I look at a number line and I say that the middle is the population mean, well, a positive 1 here is going to be 1 standard deviation above the mean. So a z-score of a 1 is 1 standard deviations above the mean. Whereas a negative 1, a z-score of a negative 1, is going to be 1 standard deviation below the mean. And the same thing happens with a 2 and a 3 that are positive, or a 2 and a 3 that are negative as well. This negative 3 here means that I am 3 standard deviations below the mean. Now, to calculate the z-score, we're going to use the formula z is equal to x, which represents our data value, minus our population mean, divided by our standard deviation. So we have our data value minus our mean, which this actually looks like our original deviation area, divided by our standard deviation. That will give us our z-score. So we take that deviation divided by the standard deviation and get our z-score. When we do this and we standardize it, this actually allows us to be able to compare things, which we will learn more about in other sections. So let's look at an example, and we're talking about fish here, specifically spotted flounder. So the mean length of a 1-year-old spotted flounder in millimeters is 126 with a standard deviation of 18. And the mean length of 2-year-old spotted flounder is 162 with a standard deviation of 28. The distribution of a flounder lengths is approximately bell-shaped. And this is going to be extremely important for us later on. Anna caught a 1-year-old flounder that was 150 millimeters in length. What is the z-score for this length? So we're given quite a bit of information here. First of all, we have the 1-year-old that has a mean length of 126 and a standard deviation of 18. We're also given the information of the 2-year-old that has a mean length of 162 and a standard deviation of 28. Well, Anna caught a 1-year-old flounder that was 150 millimeters. So she caught a 1-year-old that's 150, and we want to know its z-score. So we're going to take this 150 and we're going to subtract the 126 because that is the mean for the 1-year-olds and divide it by the 18. When I do that, 150 minus 126 is going to give me 124 divided by 18. And 124 divided by 18 is going to give me, 24 divided by 18 is going to give me a 1.333333, okay, when you do this out in your calculator. Well, when we're talking about z-scores, we always want to go to 2 decimal places. So, always 2 decimals. Even if you have to tack on zeros, you always want z-scores to end with 2 decimal places. More reasoning for that will be presented in other videos, but we want those to be in 2 decimal places. Let's continue looking at this fish story. Here, Terry caught a 2-year-old flounder whose length had a z-score of a negative 0.5. And we want to know how long this fish is. Recall from previously that the 2-year-olds had a mean length of 162 and a standard deviation of 28. Here, we do not know the we don't know the actual data value, but we do know the z value. We know that it's negative 0.5, which means this particular flounder is 1/2 of a standard deviation below the mean, which actually tells me that I should get a number less than the mean. So let's look at our formula. Z is equal to x minus the mean divided by the standard deviation. So if I plug in my numbers, I get a negative 0.5 equal to, I don't know my x, minus my mean is 162 and my standard deviation is 28, not 26. Now, I can't really solve this the way it is, so I need to do a little bit of algebraic manipulation to solve this. In order to solve this, the first thing I need to do is get rid of this denominator here. So I need to do the opposite of what it's doing. Currently it's dividing, so I'm going to multiply both sides by the 28. That way, these will cancel out. And on the right-hand side, I will strictly be left with x minus 162. On the left-hand side, I need to multiply 28 times a negative 0.5, which is basically saying 1/2 of 28, which will leave me with a negative 14. Now, I still need to get x by itself, and I have x minus 162. The opposite of subtracting 162 is going to be adding 162 to both sides. Now you have to be careful right here because you have positive and negative values. So you have a negative 14 plus 162, and that actually comes out to a positive 148. So this fish was 148 millimeters in length. So 148 millimeters long. Now if I go back to the previous example, talking about Anna's fish, we had a z-score of 1.33, and it was positive. This means that Anna's fish is 1.33 standard deviations above the mean, which that should make sense because notice her fish is longer than the mean. So we should get a positive value. Now, we can compare the z-score with the empirical rule. If you recall previously from the empirical rule, because the z-score works best if the histogram for the population is approximately bell-shaped. And we can look at those same things as I was drawing that number line previously. We can say that the center is going to be our mean, and between -1 and +1 is going to be approximately 68% of our data. Then, because that's one standard deviation, then between a -2 and a +2, that will be 95% of our data. So a z-score of a -2 and a +2. Then we can look at the -3 to the +3, and that will be all or almost all of our data will be between -3 and +3. And this follows our empirical rule regarding the standard deviations. And this is the reason why the z-score works best if the population has an approximately bell-shaped curve. Try some examples with the z-score, and if you have any questions, please let me know.